Let's begin with a quiet question. Have you ever looked up at the vast dark sky filled with countless stars and simply wondered, why is there all of this enormous, complicated, beautiful universe instead of just nothing? How did it all begin? It is perhaps the most ancient question human beings have ever asked. It's a thought that connects every one of us across all of time. When we ponder the birth of everything, we are not just looking at distant physics, we are looking for our own ultimate origin story. It feels personal, almost intimate to think about the single moment that gave rise to the galaxies, the planets, the atoms in our bodies, and even the consciousness that allows us to ask the question in the first place. This is not just a story of science, but the story of us. So let's take that journey together. Let's travel backward in our minds past the formation of Earth, past the first stars, past light itself to the very first instant of existence. When we try to picture this beginning, the name we use, the Big Bang, is perhaps the most unhelpful and misleading in the history of science. It instantly creates an image of a colossal firework, a bomb exploding outward into a pre-existing dark, empty void. But this picture is fundamentally wrong. The single most important thing to understand about the Big Bang is this: it was not an explosion in space, it was the expansion of space itself. There was no outside for it to explode into. There was no dark, empty room waiting to be filled. The room itself, all three dimensions of space and the dimension of time, came into existence in that moment. A useful though imperfect analogy is to think of the surface of a balloon. Imagine you paint thousands of tiny dots on a deflated balloon, then you begin to blow it up. From the perspective of any single dot, all the other dots are moving away from it. But the dots are not flying across the balloon's rubber surface. The surface itself is stretching, carrying the dots along with it. Furthermore, there is no center to this expansion on the surface. Every dot sees itself as the center of the expansion. Our universe is like that, only in 3 dimensions instead of the balloon's 2. The Big Bang was the moment the inflation of this balloon began. So what was the universe like at that very first moment? If we run the movie of this cosmic expansion backward, we see all the galaxies rushing back together. They merge, the stars and gas within them compress, and everything gets hotter and hotter. If we rewind the film all the way, all the matter and energy of the entire observable universe, every galaxy, every star, every atom is crushed together into a region of unimaginable density. Our current theories suggest this starting point was a singularity. This is a word scientists use when their own mathematics breaks down. It describes a state that defies our language and our imagination, a point with theoretically infinite density and infinite temperature, all crammed into a space with 0 volume. In this extreme furnace, the very laws of physics as we know them, the rules that govern gravity, light and matter, simply cease to apply. Einstein's great theory of gravity, general relativity, and the rules of the subatomic world, quantum mechanics, give different nonsensical answers. It is a state before physics as we know it, a condition of pure, incomprehensible energy before matter even existed. This concept of a singularity leads to the most mind-bending question of all. What happened before the Big Bang? What was there? The answer is perhaps the most profound in all of cosmology, and it challenges the very way we think. The answer is likely nothing. But nothing here does not mean an empty dark void waiting for a spark. It means the question itself might not make sense. The great physicist Stephen Hawking famously compared this to asking, what is north of the North Pole? The question sounds logical, but the concept of north is defined by the North Pole. It's the point where all lines of longitude meet. You cannot go further north. In the same way the Big Bang is thought to be the origin point of time itself, time is a property of the universe just like space. It is woven into the fabric of reality, what scientists call space-time. There was no ticking clock before the universe began, because there was no before. Time itself began with the Big Bang. The universe didn't appear in time, time appeared with the universe. The basic idea of the Big Bang beautifully explained why galaxies are moving apart. But in the 80s, scientists realized it had some serious problems. For example, when we look at the universe, it's incredibly uniform. The temperature of the oldest light we can see is almost exactly the same in every direction we look. This is a huge puzzle. Regions of the universe on opposite sides of our sky are billions of light years apart. They've never had time to talk to each other, or mix their energy, not even with signals traveling at the speed of light. So how did they all know to end up at the exact same temperature? To solve this, a theory called cosmic inflation was proposed. It suggests that in the very first tiniest fraction of a second, a period of time so short it's hard to even write down something like a millionth of a billionth of a billionth of a billionth of a second, the universe underwent a period of violent exponential growth, driven by a powerful unknown energy field. The fabric of space itself stretched at a rate vastly faster than the speed of light. This doesn't break Einstein's rules because nothing was travelling through space faster than light. Rather, space itself was being created and stretched. In this incomprehensible instant, a region smaller than a single proton was blown up to be larger than a grapefruit. This explains the temperature problem. Our entire observable universe was once a tiny connected patch, able to reach a uniform temperature, before inflation suddenly and violently blew it up to an enormous size. This period of hyperexpansion did something else. It planted the seeds for all the structures we see today. The world of the very small, the quantum world, is not a calm, smooth place. It is a jittery, chaotic foam. Even in a perfect vacuum, tiny fluctuations of energy called quantum fluctuations constantly bubble up with tiny particles of matter and antimatter popping into and out of existence for fleeting moments. This is the background noise of reality. During the normal expansion of the universe, these tiny fluctuations would just average out and disappear. But during inflation, the expansion was so fast and so violent that it grabbed these microscopic subatomic fluctuations and stretched them out to astronomical, even cosmic scales. A tiny random quantum hotspot was instantly magnified to be light years across. A cold spot was stretched just as large. Inflation effectively made the random fuzziness of the quantum world visible on the scale of the entire universe. These magnified fluctuations were the seeds of structure. The regions that were by pure chance slightly denser had slightly more gravity. Over the next hundreds of millions of years, gravity patiently did its work. It pulled more and more matter into these slightly denser regions. These were the fertile grounds where the first massive clouds of gas collected, where the first stars ignited, and where eventually the great clusters of galaxies, including our own Milky Way, would form. Every star and every galaxy we see in the night sky began as a single random quantum twitch in the first instant of time. Let our journey continue, leaving the shore of absolute stillness and stepping into the very first moments of existence. The quiet we just imagined was the endpoint, the destiny. The beginning, however, was anything but quiet. It was a roar of such intensity that light itself was trapped, a storm of pure, unimaginable energy. In this infant universe, in the first fraction of a second, there was no stuff, there was no matter, there were no atoms, no stars, not even the smallest speck of dust. There was only potential, there was only a perfect, unified, brilliant field of energy. You and I, the chair, you might be sitting on the air, you are breathing the distant moon. We are all made of matter. We think of matter as solid, as real. But the great insight, the secret whispered by the universe itself, was captured in a simple, elegant phrase: energy equals mass times the speed of light squared. What does this truly mean for us in this quiet moment? It means that energy and matter are not different things. They are two faces of the same coin. Energy can become matter, and matter can become energy. In the beginning, the universe was all energy. It was a bank account with an infinite balance ready to be spent, ready to be converted into the currency of reality. As this incredible, compressed, hotter than anything imaginable energy began to expand the bang itself, it also began to cool. And as it cooled, something miraculous happened. The transformation. The energy began to freeze. It condensed like breath on a cold window, and in doing so, it became the very first fundamental particles. Imagine a soup hotter than the center of a billion stars, a chaotic, churning, primordial soup. This is what we call the quark-gluon plasma. It's a state of matter so strange, so alien, it's almost impossible to picture. In this state, the fundamental building blocks of everything tiny particles called quarks, and the particles that carry force called gluons were zipping around freely. They were unbound. They were wild. In this plasma, nothing could stick together. It was too hot, too violent. If two quarks tried to join, they were immediately ripped apart by the sheer energy of their surroundings. This was a time of perfect chaotic freedom. But it could not last. The universe continued its relentless expansion, and with expansion comes cooling. Think of a gas escaping a canister. It gets cold. The universe was doing the same, but on a scale that defies imagination. As the temperature dropped just a millionth of a second after the beginning, a critical point was reached. The soup was no longer hot enough to keep the quarks apart. The forces that bind things together began to win. The quarks which had roamed free were now captured. They began to cluster together, grabbing onto each other in groups of 3. And just like that, the first things we would recognize were born. The first protons, the first neutrons. The universe was no longer just a chaotic plasma. It now had the ingredients for matter. It had created the positive core of a future hydrogen atom, a proton. It had created the neutral particle that would one day sit beside it in the heart of a helium atom, a neutron. The building blocks were formed, but the building had not yet begun. The universe was still incredibly hot and dense, a fog of these new particles along with others like electrons all bathing in a sea of intense light. But the cooling continued. Seconds ticked by, 1 second, 2 seconds. When the universe was about 3 minutes old, it reached another magic threshold. The temperature had dropped enough to a mere billion degrees that the newly formed protons and neutrons could do something remarkable. They could survive a collision. Before this, if a proton and a neutron happened to collide and stick together, a particle of high-energy light would instantly blast them apart. But now the light was just cool enough, just gentle enough that when they stuck, they stayed stuck. The universe became a nuclear furnace, a cosmic reactor spanning all of creation. This period is what we call Big Bang nucleosynthesis. It is a grand name for a very simple, very elegant process. It was the universe's first act of cooking. For the next several minutes, this cosmic furnace burned. Protons, which are just the nucleus of a hydrogen atom, fused together. A proton would capture a neutron. Sometimes 2 of these pairs would find each other. When the fires of this first furnace finally cooled, the recipe of the universe was set. The cosmos had taken its vast supply of raw ingredients and cooked them into the very first elements. What did it make? It made overwhelmingly hydrogen. Simple single-proton hydrogen. Most of the protons were left over destined to be the fuel for the first stars. It also made helium. Almost all the neutrons ended up locked away inside helium atoms, typically with 2 protons. About a quarter of all the matter in the universe was turned into helium in just these first few minutes. And as a tiny, tiny leftover, the universe cooked up a minuscule trace of lithium, hydrogen, helium, and a whisper of lithium. That's it. That was the menu. After just a few minutes of creation, the entire universe was filled with a hot, expanding, and utterly dark fog made of only these 3 simple elements. Every star that would ever shine, every galaxy that would ever spin, every planet that would ever form would have to be built from this simple 3-ingredient recipe. The great cosmic kitchen had closed. The furnace cooled. The light was still trapped in the fog, but the foundations were laid. The matter that would one day become you had been forged. And now, after this flurry of creation, a new era began. An era of waiting. An era of darkness. The universe, having just cooked the stuff of stars, now had to wait for the stars themselves to be born. It settled in for a long, quiet, dark age as the fog of creation slowly continued to expand and to cool and to wait. Let your mind settle and let us drift back into our story. We have passed the first fiery instant. The universe is born, but it is not the universe we know. It is not a place of stars. It is not a place of darkness. For a long, long time, for nearly 400,000 years, the universe is a fog. Imagine, if you will, being suspended inside a cloud. But this cloud is not made of water. It is a cloud of pure energetic soup. A plasma. It is hotter than the surface of any star. It is brighter than a billion stars. A blinding, white-hot fog that fills everything. There is no outside to look in. There is no edge. There is only this intense, glowing, restless fog. This is the opaque universe. It is opaque because light cannot travel. In this hot, dense soup, we have the building blocks of matter, the nuclei of atoms, like hydrogen and helium, and a sea of free-wild electrons. They are zipping around, energized by the incredible heat. And light particles, the photons, are also there. They are born from the energy, but the moment a photon comes into existence, the moment it tries to travel, it slams into one of those free, frantic electrons. Imagine trying to walk in a straight line through an impossibly dense, chaotic crowd where everyone is running. You take one step and you are immediately knocked in a new direction. This was the fate of light. It was scattered, endlessly. It was trapped, bouncing from electron to electron, never able to make a journey. The universe was full of light, but it was a prison of light. There was no view, there was no distance, there was only the immediate blinding chaos. Let's just rest in that idea. A universe of pure trapped brilliance, a fog of creation for 380,000 years. It's a number that is hard to hold in our minds. Let's not try. Let's just feel the time. A long cosmic childhood. A a time of chaos and heat and restless trapped energy. But all things change. The universe, from its very first moment, has been doing one thing perfectly. It has been expanding, growing larger second by second, and as it expands, it cools. Think of a hot steam. As it expands, it thins out. It cools. The same was true for the cosmos. The frantic, raging heat of the beginning was diluted by this constant expansion. The universe was stretching and cooling. The roar of creation was softening, becoming a hum. The electrons, which had been so wild and energetic, were slowing down. They were losing their frantic energy. The universe was calming. It was growing up. And then, after 380,000 years of this hot, chaotic fog, the universe cooled to a very special temperature, a temperature of about 3,000 degrees. This was the magic number. It was the moment the fog was finally ready to clear. We call this moment recombination. It is not a violent event, it is a quiet one. It is a moment of connection, a settling. All of those free-roaming electrons, all that negative energy, they are now moving slowly enough. And the nuclei, the positive hearts of hydrogen atom, they are waiting. They have been waiting. And now the attraction, the fundamental pull between positive and negative, can finally win. The heat is no longer strong enough to keep them apart. An electron finds a proton. It doesn't crash. It settles. It is captured by the proton's gentle pull. It begins to orbit, and in that moment the two frantic charged particles become one calm, stable, neutral atom. The first atom of hydrogen is born. And this is not just happening in one place, it is happening everywhere, all across the cosmos. Billions upon trillions of electrons are finding their partners. They are pairing up, they are settling down. The wild charged plasma, the soup that scattered light, is gone. In its place is a vast, calm, transparent cloud, a cloud of neutral hydrogen gas. It is the great collective sigh of the universe. The end of the primal chaos. Imagine the feeling of a high fever finally breaking. The frantic energy drains away, replaced by a profound, cool clarity. The universe has fundamentally changed. The storm has passed. And what of the light? What of all those photons that were trapped in the fog? They are free. The crowd is gone. The electrons that scattered them are now safely bound inside atoms. The obstacles have vanished. And so in this one magnificent moment, all of that trapped light, the light from the original fireball, is released. It is let go. For the very first time, light can travel in a straight, uninterrupted line. The universe, in an instant, becomes transparent. This is the first light we can ever see. It is the oldest light in existence. It is the light that was unshackled from the 380,000-year-old fog. At the moment it was released, it was a brilliant, warm, golden orange glow. It filled the entire cosmos. It was the afterglow of creation itself. And this light began its journey. It began a journey across a newly transparent, empty universe. A journey that has been going on and on and on. A journey that has lasted for 13.8 billion years. And the most amazing part, we can still see it. That exact light. It has been traveling towards us for the entire history of the universe. It is here right now. It is all around us. It fills this room. It is passing through you. But the universe has not stood still. It has continued to expand. And as space itself has stretched, it has stretched that light. The light's wavelength, its colour, has been pulled and stretched. From that warm golden glow, it has been stretched and stretched and stretched, all the way past red, past infrared, until today it is in the microwave part of the spectrum, invisible to our eyes but not to our instruments. We call it the cosmic microwave background, the CMB. When our radio telescopes look out at the space between the stars, they find it. In every single direction they look, there it is, a faint, persistent, ancient glow, the oldest photograph possible. It is the baby picture of our universe. It is an image of the cosmos, not as it is today, but as it was when it was a newborn, just 380,000 years old. A snapshot of the moment the fog cleared. And this picture, this light, is a treasure. Because it is not perfectly uniform, it is not perfectly smooth. When we look at it with sensitive instruments, we see tiny, tiny variations. Tiny ripples. Some spots are just the tiniest fraction of a degree warmer, some are the tiniest fraction cooler. These are the imperfections from the very beginning, the gurgles of the infant universe. These tiny ripples, these subtle differences in density, they are the seeds of everything that is to come. They are the spots where matter was just slightly more dense. The places where gravity, in the long eon to come, would have just a little more to pull on. These ripples are the blueprints for the future. The blueprints for galaxies, for stars, for us. But, no. Not yet. The fog is gone. The universe is transparent. The first light, the CMB, is released and is now sailing across space, cooling and stretching. The universe is now a vast, dark, transparent ocean of neutral hydrogen gas. And it is dark, utterly profoundly dark. This is the beginning of a new era, an era we call the Cosmic Dark Ages. It is dark because the first light, the CMB, has already stretched out of the visible spectrum. It's a microwave glow, not a visible one, and there is nothing else, nothing at all to make new light. Not one single star has been born, not one galaxy has formed. Imagine a silence, a stillness, a darkness, an ocean of invisible gas expanding in the cold. The universe is now waiting. The stage is set, the lights are off, the actors are not yet born. This darkness, this quiet, lasts for a very long time. For 100 million years, perhaps 200 million years. It is a vast, empty, quiet night, a time of perfect, uninterrupted peace. But it is not a dead time, it is a time of hidden, patient work. In the dark, something is happening, gravity. Remember those tiny ripples, those seeds in the baby picture. In the dark, gravity is beginning its slow, patient, relentless work. The places that were just slightly denser, they have just a little more gravity, and so they pull just a little on the gas around them. And as they pull in more gas, they become denser still. And as they become denser, their gravity grows stronger, and they pull in more gas. A slow, invisible, powerful dance is beginning in the dark. The gas of the universe is not smooth. It is beginning to clump, to gather, to collapse in on itself in massive, massive clouds. This is the great preparation. The universe is gathering its breath. It is collecting its materials. It is building the foundations. These clouds of hydrogen, growing denser and denser in the long dark night, are the wombs where the first stars will be born. The dark ages are not an ending. They are a necessary pause, a quiet interlude, a time for the universe to prepare for the next great act. It is preparing to turn on the lights. So let your mind rest in that darkness, not a scary darkness, but a calm, quiet, expectant darkness, a darkness full of potential, a darkness where the seeds of galaxies are slowly being drawn together. The universe is at peace, but it is not asleep. It is dreaming of the light to come. Breathe in and feel the stillness of that long cosmic night. Breathe out and let go of the day. The universe is patient, and in its patience it is building wonders. The first light is just around the F corner. But for now, there is just the calm, the dark, and the slow gathering silence. For hundreds of millions of years, the universe was filled with a neutral, transparent fog of hydrogen and helium, but it was not perfectly smooth. The map of the first light, the cosmic microwave background, showed us the blueprints. It had tiny ripples regions that were just slightly, almost impossibly denser than others. We are talking 1 part in 100,000. In this vast darkness, the quietest, most patient force in the cosmos began its work: gravity. Gravity is a simple force, it pulls things together. And in this early universe, it had a simple job: find the spots that were slightly denser and make them even denser. This process is incredibly slow, a silent, patient accumulation. A region with a tiny bit more mass has a tiny bit more gravity. This extra gravity pulls in a little more gas from its surroundings. Now it has even more mass and even more gravity. It's a rich, get-richer scenario playing out over millions of years in the dark. Gravity was the architect, and it was drawing the plans for the first great structures. But astronomers who studied this process found a massive problem. The universe is expanding, and that expansion works against gravity. It's constantly trying to pull things apart. When scientists did the math, they realized something alarming using only the gravity from the matter. We can see the hydrogen and helium gas there simply was not enough time. The universe's expansion was too fast, and the pull of normal gravity was too weak. By this math, the great galaxies we see today, including our own Milky Way, should never have had time to form. Gravity needed help, it needed more gravity. And that help came from a source that is, to this day, the biggest mystery in cosmology. We got our first clue when we looked at our neighbours. When astronomers like Vera Rubin studied nearby spiral galaxies in the 1970s, they measured how fast the stars were moving. They expected a simple result. In our solar system, the planets closest to the Sun, like Mercury, move the fastest, while distant planets like Neptune move slowly. This is because the vast majority of the mass the Sun is at the centre. Galaxies should be the same. Most of the bright visible matter, the stars, is in the centre. Stars on the outer edges should be moving much, much slower, but they weren't. Against all expectations, the stars on the very edges of galaxies were moving just as fast as the stars near the centre. It was shocking. The only way this is possible is if the galaxy is spinning inside a massive invisible ball of something whose gravity is holding those speeding stars in their orbits, preventing them from being flung off into intergalactic space. But the stars we see were just the visible tip of a much larger invisible iceberg. This wasn't the only evidence. Astronomers also use a technique predicted by Albert Einstein. He showed that mass gravity can bend light. If you have a massive object like a cluster of galaxies, it will act like a giant cosmic magnifying glass. Any light from a more distant galaxy passing by it will be bent, warped, and magnified. This is called gravitational lensing. When we pointed our telescopes at these massive clusters, we saw the lensing. The images of distant galaxies were smeared into beautiful arcs and rings. But when we calculated the mass of all the visible matter in the cluster, all the stars, all the gas, it wasn't nearly enough to create the warping we saw. Not even close. We needed 5 to 6 times more mass than we could account for. This invisible, mysterious something was everywhere. It provided the extra gravity to hold galaxies together. It provided the extra mass to bend light. But it didn't shine. It didn't reflect light. It didn't block light. It didn't interact with atoms or particles in any way we could measure. It just existed. We gave it a name, dark matter. This dark matter is the invisible architect, and it solves the problem of how the universe formed so quickly. Here's how. In the very early universe, the normal matter, protons and electrons, was tied up with light. It was a hot, buzzing plasma. This hot matter felt an outward pressure from the light which fought against gravity's pull. It was hard for normal matter to clump. But dark matter didn't have this problem. It doesn't care about light. It is cold. It felt no outward pressure. So while normal matter was stuck fighting the expansion, the dark matter got a head start. For millions of years before the first light was released, the dark matter was already clumping. It was silently building the scaffolding of the universe. It collapsed under its own gravity, forming vast invisible halos, like giant invisible gravity wells dug in space. When the universe finally cooled and the cosmic microwave background was released, the normal hydrogen gas was finally set free. The pressure was off. This gas, which had been spread thin, immediately began to fall, and it fell right into the gravity wells that the dark matter had already prepared. The dark matter acted as the mold, and the normal matter was the material poured into it. This invisible scaffolding wasn't random. Computer simulations show that this dark matter formed a breathtakingly beautiful structure, the largest structure in the cosmos. We call it the cosmic web. Imagine a 3-dimensional spider web filling the entire universe. It is made of 3 parts. There are long, thin, twisting filaments like cosmic rivers of dark matter and gas. There are the nodes, the busy intersections where these filaments meet. These nodes are the deepest gravity wells, the places where the most matter collected. And then there are the voids, the vast, empty regions between the filaments where matter was drained away to feed the growing structures. This is the architecture of our universe. The galaxies we see are not scattered randomly in space like marbles on a floor. They are painted onto this invisible web. Galaxies form along the filaments like strings of pearls, and where the filaments cross at the nodes, they form massive galaxy clusters. Our own Milky Way galaxy is not alone. It is travelling along a filament. The voids are the great deserts of the cosmos. The invisible architect had done its job. It had laid the foundations. It had built the highways and the intersections. It had gathered the raw material, the hydrogen and helium gas, into the densest nodes of its invisible web. Everything was now in place. All that was missing was a spark to light the fuse. The first stars were about to be born. For an almost endless time, the universe was waiting. After the initial flash of its birth, a profound quiet had fallen. This was an era of darkness, a darkness that lasted for hundreds of millions of years. The cosmos was filled with a thin, invisible mist of hydrogen and helium gas drifting silently through an invisible scaffolding of dark matter. There were no stars, no planets, no light. There was only the cold, the quiet, and the patient pull of gravity. But in this stillness, something wonderful was beginning. Imagine vast invisible clouds of this dark matter spread throughout the cosmos. They are the skeleton of the universe. And their gravity, though gentle, is persistent. Slowly, patiently, they began to pull in the floating hydrogen gas. Like cosmic tributaries flowing into unseen rivers, the gas began to gather. Over millions of years, in the densest pockets of this dark matter framework, the gas clouds grew heavier, denser, and more compact. Inside these collapsing clouds, the pressure began to build. The atoms of hydrogen gas, once floating freely, were now squeezed together, colliding with more and more energy. The core of the cloud grew hot. Not just warm, but millions of degrees hot. Hot enough for a new kind of fire to ignite. And then it happened. In thousands of places across the dark universe, the first lights blinked on. The crushing pressure at the heart of these massive gas clouds triggered nuclear fusion. Hydrogen atoms began to slam together, forging helium, and in that process, releasing a tremendous flood of energy, light. The first stars were born. The long cosmic night was over. The universe at last had awakened. These were not stars like our sun. We call them population 3 stars, the first generation. They were giants, monsters of unbelievable scale. Imagine a star not just 10 or 20 times heavier than our sun, but hundreds of times heavier. They were made of almost pure hydrogen and helium, the raw, unprocessed material of the early cosmos. Because they were so massive, their cores burned with an intensity that is difficult to comprehend. They were not a gentle yellow-white like our sun. They were a brilliant, searing blue-white. They blazed with the light of millions of our suns combined. For the first time, the universe was filled with light, casting long, dramatic shadows across the gas clouds from which these stars had been born. But this incredible power came at a price. These giant stars lived fast and died young. While our own sun will live for 10 billion years, these first giants burned through their immense fuel supply in just a few million years. A mere heartbeat in cosmic time, they were the universe's first magnificent and fleeting spectacle. But their short, brilliant lives were not in vain. They were not just sources of light, they were the universe's first forges. Inside the core of every star, a kind of alchemy takes place. The immense heat and pressure is a cosmic furnace. These first stars took the simple elements they were born with, hydrogen and helium, and began to cook them into something new. They fused hydrogen into helium, and when that was spent, they fused helium into carbon. They forged carbon into oxygen, and oxygen into neon, magnesium, and silicon. And in the very largest of these stars, the process continued all the way up to iron. Think of that. Carbon, the very element that forms the basis of all known life. Oxygen, the element we breathe to survive. Iron, the element that flows in our blood. Before these stars, none of this existed. The universe was simple, sterile. These stars, in their brief, violent lives, were creating the very building blocks of the future. They were the ancestors of everything complex, everything interesting, and everything alive. But how did these new precious elements get out? They were trapped deep inside the stars. This is where the second act of their lives began their death. When a star this massive runs out of fuel, the outward push of its nuclear fire instantly ceases. Gravity, which had been held at bay for millions of years, wins. In an instant, the star's core collapses catastrophically. This collapse triggers the most powerful event the universe had yet seen, a supernova. The first supernova. The star tears itself apart in an explosion of unimaginable violence. An explosion so bright it could briefly outshine an entire galaxy of stars yet to be born. This final glorious act was not an end, it was a gift. The explosion blasted all those new heavy elements, the carbon, the oxygen, the iron, and everything else they had forged far out into the surrounding space. Like a cosmic gardener scattering seeds, these first supernovae enriched the universe. They seeded the neighbouring clouds of hydrogen gas with new, heavier ingredients. The next generation of stars would not be born from pure hydrogen and helium. They would be born from this enriched, recycled gas. They would have these new elements which would allow them to form planets, to form rocky worlds, to form the complex chemistry that life requires. And what happened to the very largest of these giants? The ones so massive that not even a supernova could halt their collapse. For them, a different fate awaited. When their fires went out, gravity won completely and irreversibly. They collapsed and kept collapsing. The core was crushed past all known limits, smaller than an atom, denser than anything imaginable, until it punched a hole in the fabric of space and time itself. They became the first black holes. These were not yet the supermassive monsters we now find at the hearts of galaxies. They were just the seeds, but they were seeds of immense gravity. They would remain patiently waiting in the dark, pulling in matter growing larger over billions of years. They would become the anchors, the gravitational centers around which the first great galaxies would one day begin to spin. The awakening was complete. The darkness had been broken. The universe was no longer simple. It was now seeded with heavy elements, the stuff of planets and of life. It was now dotted with the first black holes, the seeds of future galaxies. The cosmic stage was set, and the great story of construction, of complexity, and of us was finally ready to begin. After hundreds of millions of years of complete and total darkness, the long dark ages of the universe finally came to an end. The silence was broken as gravity, working slowly and patiently in the dark, finally gathered the primordial clouds of hydrogen and helium gas into clumps dense enough and hot enough to ignite. This moment when the first points of light pierced the cosmic gloom is known as the cosmic dawn. These were not stars like our sun. They were the very first generation known as population 3 stars. They formed from gas that was pure, containing only the light elements created in the Big Bang. Because they lacked the heavier elements that help modern stars cool down, they grew to monstrous sizes, becoming hundreds of times more massive than our sun. And because they were so massive, they were unimaginably hot, blazing with a fierce, brilliant light. They burned through their fuel in only a few million years, a mere blink of an eye in cosmic time. But during their short, violent lives, they flooded their surroundings with incredible amounts of high-energy radiation, particularly ultraviolet UV light. At this time, the vast majority of the universe was still filled with a thick, cold fog of neutral hydrogen gas. This fog was opaque. Just as the car's headlights are scattered by a dense fog on Earth, this cosmic fog stopped light from travelling freely across space. When the intense UV light from these first stars began to shine, it was like turning on the first headlights in this universe-spanning mist. This light immediately began to have a dramatic effect on the fog around it. This powerful UV light carried enough energy to fundamentally change the nature of the universe. This is the process of ionization. The name is important. It means the universe was ionized again. The first time was in the universe's first 380,000 years, when it was a hot, dense plasma of free protons and electrons. Then it cooled, and those protons and electrons combined to form the neutral hydrogen fog of the Dark Ages. Now the new stars were providing the energy to reverse that process. Here is how it worked. A particle of high-energy UV light, a photon, would travel from a new star and strike a neutral hydrogen atom, which is one proton and one electron bound together. The photon's energy was so high that it would physically zay or rip the electron completely away from the proton. The atom was now ionized, split back into its free-swimming parts. A single hot, massive star could ionize a vast amount of the gas around it. This process didn't happen everywhere at once. It started in bubbles. Each of the first stars, or the first small clusters of stars, carved out a bubble of clear, transparent ionized gas in the great neutral fog. As more and more stars were born, their individual bubbles grew larger and larger. Eventually, these expanding bubbles started to touch and overlap, merging into one another. Over hundreds of millions of years, these bubbles grew until they had joined together, and the entire fog of neutral hydrogen between the galaxies was completely burned away. The universe, for the first time since its infancy, became transparent to light. This is the single most important reason we can see distant galaxies today. Their light can finally travel billions of light years across a clear cosmos to reach our telescopes. While this cosmic fog clearing was happening, the universe was also building its first major cities. The formation of early galaxies was underway, driven by the combined forces of gravity and the life cycles of these first stars. Gravity was the master architect. The invisible scaffolding of dark matter that had been clumping together during the Dark Ages provided the gravitational foundation. These massive halos of dark matter pulled in the hydrogen and helium gas from their surroundings, providing the fuel for the first stars. But the first stars themselves were also crucial ingredients. When these massive population 3 stars died, they exploded as supernovae. These were some of the most powerful explosions the universe has ever seen. These explosions did two critical things. First, they blasted the surrounding gas, sometimes pushing it out of the small proto-galaxies and temporarily slowing down the birth of new stars. But second, and far more importantly, these explosions were the cosmic forges that created the first heavy elements. Inside their fiery cores, these stars had fused hydrogen and helium into elements like carbon, oxygen, silicon, and iron. When they exploded, they seeded the surrounding gas clouds with these new metals. This enriched gas was the raw material for the next generation of stars called population 2 stars. Because this gas now contained these heavier elements, it could cool more efficiently, allowing it to form smaller, more stable stars that could live for billions of years, stars much more like our Sun. Gravity continued its relentless work, pulling these small collections of stars, gas and dark matter together. These small proto-galaxies crashed into each other and merged, gradually building up larger and more complex structures. These were the first true, though often messy and irregular galaxies. Deep within the centers of these chaotic, newly forming galaxies, something else was growing, something mysterious and incredibly powerful. This marks the beginning of the co-evolution of galaxies and their central black holes. When we look at mature galaxies in the universe today, like our own Milky Way, we observe a very strange rule: the more massive the central bulge of the galaxy is, the more massive the supermassive black hole SMBH at its very center is. This is a profound puzzle. A galaxy is hundreds of thousands of light years across, while its central black hole might only be the size of our solar system. How does the galaxy's vast outer region know what size the tiny black hole at its core is? The only logical answer is that they grew up together, locked in a kind of feedback loop. This relationship had to start back in this early era. We are still trying to figure out how the first seed black holes formed. Perhaps they were the collapsed remnants of the very first population 3 stars, leaving behind black holes that were only 100 times the mass of the Sun. Or in some very dense, pristine gas clouds, a direct collapse might have occurred where a massive cloud of gas collapsed directly into a black hole of thousands of solar masses without ever becoming a star first. But the biggest puzzle is how they grew so fast. We have observed quasars, which are supermassive black holes feeding on gas so intensely that they outshine their entire host galaxy when the universe was very young. To get that big, that fast, they must have been eating gas at a furious and sustained rate. This feeding process itself would have had a huge impact on the galaxy. As gas spiraled into the black hole, it would form a disk that became white hot from friction, blasting out intense radiation and powerful winds. These winds would be strong enough to blow the gas out of the galaxy's center, which would shut down star formation and ironically cut off the black hole's own food supply. This push and pull created a cycle of self-regulation. The galaxy provided the gas to feed the black hole grew and turned on, and its powerful output then shut down star formation in the galaxy and its own growth. This cosmic dance, this co-evolution, is likely the secret link that forces the galaxy and its central black hole to grow in scale, together, a relationship that has shaped the structure of the cosmos for the last 13 billion years. And so we drift. We have looked out into the deep past to the echoes of the beginning. Now, let us turn our gaze inward. Let us journey back home, not just to our world, our small blue planet, but to the grand city of stars we belong to. When you look up on a clear night far from the lights of human cities, you see it. A faint glowing band of light stretched across the heavens. A river of light. The ancient Greeks called it Galaxius Kyklos, the Milky Circle. We call it the Milky Way. But this soft river of light is an illusion of perspective. We are not looking at it. We are looking through it. We are inside it. If we could travel impossibly far, hundreds of thousands of light years away, and look back, we would see our home for what it truly is. A breathtaking spinning pinwheel of light, a vast spiral galaxy, is an immense structure 100,000 light years from one edge to the other. A city of at least 100 billion stars and perhaps as many as 400 billion. 400 billion suns, each one potentially with planets of its own. Our galaxy is a giant, but it is just one island in an immeasurable cosmic ocean. As we look out, we now know there are perhaps 2 trillion other galaxies in the observable universe. 2 trillion. Each one an island of stars separated by gulfs of darkness so vast that light itself takes millions or billions of years to cross them. Our Milky Way was not born this way. It did not appear fully formed. Like a great city, it was built over time. It grew. Over 13 billion years, it has pulled in and merged with countless smaller galaxies, great clouds of gas and streams of dark matter. It is a process of accretion, a slow gravitational assembly that continues even today. Our galaxy is still slowly, patiently swallowing smaller dwarf galaxies, adding their stars to its own brilliant collection. It is a living structure, constantly changing, constantly swirling. And the stars within it, they tell a story of generations. The very first stars in the universe were born from clouds of almost pure hydrogen and helium, the simple elements forged in the Big Bang. These firstborn stars were giants living fast, brilliant, and violent lives. They burned through their fuel in only a few million years before exploding in the most powerful blast the universe has ever known, supernovae. In those unimaginable furnaces, in those final fiery moments, these stars forged something new. They crushed simple atoms together to create heavier elements: carbon, oxygen, silicon, iron. These new elements, the building blocks of complexity, were blasted out into space. They seeded the surrounding clouds of gas. The next generation of stars was born from these enriched clouds, and when they died, they scattered even more heavy elements. Our Sun is a child of this lineage. It is a second or perhaps third generation star. It was born about 4.5 billion years ago from a nebula that was already rich with the ashes of countless stars that had lived and died before it. This means that every heavy element in our world, every atom of carbon in your body, every atom of iron in your blood, every atom of calcium in your bones, was created long ago in the heart of a massive star that is now long gone. We are in the most literal sense the children of the stars. We are stardust given consciousness. We are the universe reflecting on itself. So where are we in the vast spinning city of stardust? The centre of our galaxy, like most large galaxies, is a place of intense activity. It is brilliant and chaotic. At its very heart, hidden from our eyes by thick clouds of dust and gas, lies a supermassive black hole. We call it Sagittarius A star, pronounced Sagittarius A star. It is a monster of gravity weighing as much as 4 million of our suns. Billions of stars are crowded around it, orbiting at incredible speeds. But we are not there. We do not live downtown. We live far from that chaotic centre. Our solar system is located in the galactic suburbs. We are nestled in a smaller partial spiral arm known as the Orion Arm or the Orion Spur. It is a quiet neighbourhood. We are about 26,000 light-years away from the galactic centre, roughly 2/3 of the way out toward the edge. This quiet location may be one of the reasons life had a chance to flourish here. We are far from the intense radiation of the galactic core. We are not crowded by other stars that could disrupt our solar system's delicate balance. We are in a safe, stable region perfect for a planet to spend billions of years patiently, slowly developing life. We are on a gentle cosmic journey. Our entire solar system is orbiting the centre of the Milky Way, but it's a slow, long orbit. It takes us about 230 million years to make one single lap. The last time our solar system was in this part of the galaxy, the first dinosaurs were just beginning to walk the Earth. And even here in our quiet suburb, we are not alone. Our Milky Way is the senior member of a small cluster of galaxies we call simply the local group. We have neighbours. Orbiting our Milky Way like moons around a planet are several smaller dwarf galaxies. The most famous are the Large and Small Magellanic Clouds, visible as faint cloudy patches in the night sky of the southern hemisphere. They are gravitationally bound to us, but this is a dangerous dance. Our galaxy's immense gravity is slowly pulling them apart, and over the next few billion years they will be completely absorbed, their stars merging with our own. And then there is our great companion, our twin, the Andromeda Galaxy. It is the most distant object you can see with your unaided eye. A tiny, faint, fuzzy patch of light. It is another great spiral galaxy, much like our own, perhaps even a little larger. It sits 2.5 million light-years away, but it is not standing still, and neither are we. Pulled by the inescapable force of our mutual gravity, we are moving toward each other. The Andromeda Galaxy is falling toward the Milky Way at a speed of over 100 kilometers every second. This is our galaxy's long-term destiny. In about 4.5 billion years, this slow, steady gravitational dance will become a great merger. It will not be an explosion. The spaces between the stars are so vast that it is incredibly unlikely any two stars will actually collide. Instead, the two grand galaxies will pass through each other like two magnificent ghosts of light. Gravity will twist and warp them, pulling long streamers of stars and gas out into space. Then over hundreds of millions of years, gravity will pull them back together, and then they will merge again and again until they finally settle. They will combine to form one single new enormous elliptical galaxy. The night sky for any observer then will be transformed a brilliant new starscape. But that is a story for a different time, a future so distant it is almost imaginary. For now, just feel the quiet motion. Feel our Earth turning gently, feel our solar system drifting through the calm, safe suburbs of the Orion Arm, and feel our entire galaxy, our great spiralling home, turning silently in the vast, peaceful dark. Our story continues, not on Earth, but billions of years before Earth even existed. The universe was already ancient, filled with stars that had lived and died. Around 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, there was no sun, no planets, and no life. There was only a vast, dark and cold cloud of gas and dust floating in space. This was no ordinary cloud. It was a nebula, a cosmic nursery, and it held the recycled ingredients of a long-dead star. The gas was mostly hydrogen and helium, the simplest and most common elements in the universe. But the dust, tiny grains of silicon, carbon, iron, and other heavier elements had been forged deep inside a massive star that had lived its entire life and then exploded in a spectacular supernova. We are quite literally made of stardust, and this cloud was the inheritance that star left behind. For millions of years, this cloud just drifted. But then something disturbed it. Perhaps it was the shockwave from another nearby supernova, or the gravitational pull of a passing star. Whatever the cause, a part of this massive cloud began to collapse in on itself. This is where gravity, the silent architect of the cosmos, took charge. As the cloud collapsed, gravity pulled all the gas and dust inward toward a common center. Just like an ice skater spins faster when they pull their arms in, the collapsing cloud began to spin. As it spun, it also flattened out like a spinning ball of pizza dough, becoming a flat disk. The vast, messy cloud was organizing itself. The overwhelming majority of the material, more than 99.8% of all the gas and dust, spiraled into the very center. As this material piled up, the pressure became unimaginable. The atoms were squeezed so tightly that the center began to heat up, glowing a dull red. This dense, hot core was a protostar, a baby sun. It continued to gather mass, and the core got hotter and hotter, reaching millions of degrees. Finally, the pressure and temperature became so extreme that a new kind of fire was ignited. It wasn't a chemical fire like wood burning, it was a nuclear fire. Hydrogen atoms, the most basic building blocks, began smashing into each other with such force that they used to fuse together to create helium. This process, called nuclear fusion, unleashed a tremendous sustained burst of energy. This outward blast of energy pushed against gravity's inward crush, creating a perfect balance. In that moment, our star was born. The sun switched on, and its light flooded the surrounding space for the first time. But what about the tiny fraction of material that wasn't pulled into the sun? This was the leftover 1/5 of 1%. This material formed that flat spinning disk we mentioned, which now circled the young bright sun. This was the protoplanetary disk, and it was the birthplace of the planets. This disk was not a calm place. It was a chaotic swirl of gas and dust orbiting the sun at incredible speeds. And most importantly, it had a steep temperature gradient. Near the new sun, it was scorching hot. Farther out in the deep shadows of the new system, it was freezing cold. This difference in temperature is the single most important reason why our solar system looks the way it does. The process of building planets called accretion began immediately, and it was a messy, violent affair. In the beginning, there were only microscopic dust grains, the leftovers from that ancient supernova. These tiny grains orbiting the sun would gently bump into each other. At first, they just stuck together through simple static electricity, like dust bunnies clumping together under your bed. A grain stuck to another grain, then another. They grew from dust to pebbles. These pebbles continued to collide, forming larger objects the size of boulders. As they grew larger, their own gravity started to become noticeable. They were now planetesimals objects, a few miles or kilometers across, big enough to gravitationally attract other pebbles and dust in their path. Now a rich get richer scenario began. The largest planetesimals had the strongest gravity, so they pulled in the most material. They grew faster and faster, sweeping their orbits clean. This was a chaotic, destructive phase. Giant planetesimals constantly sashed into each other. But these weren't always destructive collisions. Often, they were mergers. Two objects would collide and become one larger object. Over millions of years, these planetesimals combined to form hundreds of protoplanets, baby planets roughly the size of our moon or Mars. The inner solar system was a crowded shooting gallery, with these protoplanets orbiting in unstable, crisscrossing paths. They crashed into each other in world-shattering impacts, a process known as the giant impact stage. Our own Earth was likely struck by a Mars-sized protoplanet, an impact so enormous that it blasted a huge amount of material into orbit, which eventually coalesced to form our moon. But why did these collisions create small rocky worlds in one place and giant gaseous worlds in another? It all comes back to that temperature difference in the disk. There was an imaginary boundary in the disk, known as the frost line or snow line. This line was located roughly where the asteroid belt is today, between the orbits of Mars and Jupiter. Inside the frost line close to the sun, it was too hot for materials like water, ammonia and methane to freeze. They remained in a gaseous state. The only materials that could become solid were rock silicates and metal like iron and nickel. In the grand scheme of the nebula, rock and metal were very rare. So the protoplanets forming here, Mercury, Venus, Earth and Mars, were built from these scarce heavy materials. They couldn't grow very large because there just wasn't much solid stuff to build with. They became the small, dense, rocky planets. Outside the frost line, it was cold enough for water, methane and ammonia to freeze into solid ice. This was a game changer. Ice was vastly more abundant in the nebula than rock and metal. This meant the protoplanets forming out here, the cores of Jupiter and Saturn, had access to a huge supply of building material. They grew by grabbing rock metal and all that plentiful ice. They grew massive very quickly. Soon their cores became enormous, perhaps 10 or 15 times the mass of the entire planet Earth. Once they reached this size, their gravity was so powerful that they started to do something new. They began to suck in the vast amounts of hydrogen and helium gas left over in the outer disk. This triggered a runaway effect. The more gas they grabbed, the stronger their gravity became, and the faster they could grab even more gas. They swelled into the colossal gas giants we see today. Jupiter and Saturn are essentially giant balls of hydrogen and helium, the same ingredients as the Sun, just not quite big enough to ignite nuclear fusion. Farther out, Uranus and Neptune also grew large, but the disk was thinner out there, so they grew more slowly. They collected a lot of the frozen ices, which is why they are often called ice giants, but didn't manage to capture the same massive envelopes of hydrogen and helium as Jupiter and Saturn. For millions of years, this planet building continued. Eventually, the young sun's ferocious solar wind, a constant stream of charged particles, became strong enough to blow all the remaining gas and fine dust out of the solar system, ending the era of planet formation. What was left was the system we recognize today: a single star, 4 small rocky worlds, 2 massive gas giants, 2 distant ice giants and the leftover rubble, the asteroids in the asteroid belt, perhaps a failed planet torn apart by Jupiter's gravity, and the icy comets in the far dark reaches of space. The chaotic spinning cloud had finally, after millions of years of violence and creation, become a stable, orderly system. Let us drift back, closer to home, out of the deep interstellar ocean past the neighbouring planets, to a single delicate point of light. A world unlike any other we have found. We call it the Blue Marble, our island, our home. It looks so peaceful from a distance, a serene swirl of white clouds over a deep, endless blue. But this stillness, this tranquility, is new. It was bought by an age of unimaginable violence. If you could travel back in time 4.5 billion years, you would not recognize this world. There was no blue, there was only red, a glowing, seething world of molten rock. This was the infant Earth, a planet still being formed in the chaotic construction site of the new solar system. It was not a quiet place, it was a target. The skies were filled with the debris left over from creation, asteroids and comets, and they fell in a constant fiery rain. This bombardment, this cosmic shrapnel, kept the surface of our planet liquid, a global ocean of magma, glowing like a hot coal in the darkness of space. It was a world of fire and impact, waiting for its destiny. And then came the collision that changed everything. In this young, crowded solar system, Earth was not alone in its orbital path. Another young planet, a traveller, was sharing the same cosmic neighbourhood. Astronomers have given this lost world a name, Theia. It was a formidable object, perhaps the size of the planet Mars, and its orbit over millions of years became unstable. It was drawn inevitably toward the young Earth. Imagine the scale of this, not an asteroid. A world, striking another world. It wasn't a direct hit, but a glancing, catastrophic blow. Theia struck the molten Earth, and the impact is almost beyond comprehension. It vaporized Theia completely. It vaporized a huge portion of the Earth's own mantle. The force of this collision threw a cloud, an immense expanding ring of superheated rock and vapor, into orbit around the scarred planet. The Earth itself was changed forever, tilted by the force, and spinning much, much faster. But in this destruction, there was a profound creation. The Earth, now glowing brighter than ever from the heat of the impact, was not alone. That ring of debris, the vaporized remains of Theia and the skin of the Earth, did not just drift away. Gravity, the patient sculptor of the cosmos, began its work. In that ring of fire, particles began to find each other, to cling together. Dust became pebbles, pebbles became boulders, boulders became mountains, all colliding and merging in the darkness. Over thousands of years, or perhaps tens of thousands, this chaotic ring of rubble pulled itself together, coalescing into a single massive sphere, a new world, born from the wreckage of our moon. In the beginning it was terrifyingly close. Imagine looking up into the sky and seeing this massive glowing molten ball. Perhaps 20 times larger than the moon we see today, it dominated the sky, and the Earth itself was spinning wildly from the impact. A day might have lasted only 5 or 6 hours. It was a dizzying, chaotic waltz. But the moon, our new companion, began to quiet us. Its gravity reached out. Like a steadying hand, it began to pull on the spinning Earth, acting as a brake. It slowed our rotation. That 5-hour day slowly, over hundreds of millions of years, stretched into 6, then 10, then 20, until it settled into the familiar 24 hours that governs our lives. And it did something else, something vital. The impact from Theia had knocked the Earth off kilter, giving it an axial tilt. This tilt is what gives us our seasons, but this tilt was unstable, chaotic. The Earth might have wobbled, tipped over, pointed its poles directly at the sun. This would have created a climate of impossible extremes, not a place for life. The moon, our anchor, its immense gravity grabbed hold of the Earth's wobble and stabilized it. It holds us steady. It ensures that our tilt remains constant, giving us the predictable, gentle rhythm of spring, summer, autumn, and winter. The very stability of our climate, the reason our planet is so habitable, we owe to that ancient, violent collision. And of course, it gave us the tides. As the Earth cooled and the first oceans began to form, the moon's close, powerful gravity pulled on them. It wasn't the gentle tide we know today. It was a massive, surging bulge of water, hundreds of feet high, racing around the planet as it spun. This constant, powerful mixing, this churning of the young oceans, mixing water into minerals. Many scientists believe this tidal engine was the very thing that stirred the pot, helping the first simple ingredients of life to find each other in the primordial soup. But where did that soup come from? Where did the blue in blue marble originate? The Earth was born of fire. The Theia impact would have boiled off any water that existed. Our world should have been a dry, rocky husk. The water came from two receptacles. It came from within. As the molten Earth slowly cooled, a crust began to form. But trapped beneath that crust, in the molten rock of the mantle, were vast quantities of dissolved gases, including water vapor, steam. For millions of years, the young Earth was covered in volcanoes. Millions of them. They erupted constantly, and they weren't just spewing lava, they were exhaling, releasing the planet's trapped atmosphere, carbon dioxide, nitrogen, and incredible unimaginable amounts of steam. This steam rose, cooled, and fell as rain, a planet-wide continuous deluge lasting for millions of years, slowly filling the basins, creating the first shallow hot seas. And it came from beyond. The Great Bombardment wasn't over, but now the deliveries were a blessing. For millions of years, the Earth was struck by comets, which are essentially massive dirty snowballs, frozen relics from the outer solar system. And it was struck by asteroids, which we now know often carry large amounts of water ice, trapped within their rock. The Hadean fire had passed. The Earth was now cool enough to keep what was delivered. Every impact, every shooting star, it was a delivery. A payload of warp chariot from the farthest reaches of the solar system. The very ice that formed in the darkness beyond Neptune travelled for billions of years to splash into the oceans of Earth. And so the stage was set. The red fiery world was gone. In its place, a stabilised planet, slowing its spin, held in a gentle gravitational embrace by its daughter the moon. And it was covered, draped in a global ocean, delivered from the stars, and exhaled from the heart of the planet itself. The blue marble was ready for the next, perhaps most incredible chapter, the first stirrings of life. We have spent our time looking outward into the silent, sprawling darkness dotted with islands of light. We've traced the birth of stars and the grand architecture of galaxies. But now let us turn our gaze inward and downward, back to one small, specific world. A blue-white marble cooling in the twilight of the early solar system orbiting a very average star. For eons, this planet was a dynamic but lifeless laboratory. It had oceans of water. It had an atmosphere of nitrogen, methane, and carbon dioxide. It had volcanic fire and cooling rock. It had all the ingredients, but it was still just chemistry. And then, somewhere on this historicless globe, the most profound event in its history occurred. The greatest threshold in the known universe was crossed. It is the line that separates the not alive from the alive. We call this mystery abiogenesis. It is the moment a collection of simple non-living molecules, compounds of carbon, hydrogen, oxygen, found a way to organize themselves. It's the moment chemistry learned to replicate, to metabolize, to build a boundary around itself and declare I am and you are not. How does this happen? How does inanimate matter develop an intention to survive? This question is perhaps the deepest one we can ask about our place in the cosmos. We search for the cradle, the place where this spark first caught. We have two leading theories, two very different nurseries for the first cell. Many imagine a warm little pond, as Charles Darwin first mused, a shallow pool of water perhaps on a volcanic island or near a geothermal spring. In this primordial soup, the building blocks of life, amino acids, nucleotides, could accumulate washed in by rivers delivered by comets. Energized by the raw ultraviolet light of the young sun or the crackle of lightning striking the water, these molecules would collide for millions of years. They would link up, break apart, and link up again, exploring countless combinations until one by pure chance formed a chain that could make a crude copy of itself. But there is another, more dramatic possibility. Perhaps life did not begin in the light, but in the dark. Imagine the floor of the ancient ocean miles down in the crushing absolute black. Here the planet's crust is thin and seawater seeps down, meeting the hot magma below. This water is superheated and bursts back into the ocean through cracks in the rock. These are hydrothermal vents. They look like fantastic dark chimneys billowing plumes of black mineral-rich smoke. They are oases of energy. Not energy from the sun, but pure chemical energy. A ferocious gradient exists between the scorching, acidic, hydrogen-rich water of the vent and the cold alkaline ocean around it. In the microscopic pores of this chimney rock, this energy gradient could have been the battery that powered the first metabolism. Life born in darkness, pressure and fire rather than in a gentle sunlit pond. However it began, it did begin. A single fragile cell, a bubble of persistence in a chaotic world. For more than 1 billion years, this was all of life. A planet ruled by the invisible, a teeming microbial world. And then one of these tiny beings invented a new way to live, a trick that would fundamentally rewrite the planet. A type of bacteria floating in the shallow seas evolved the ability to do something revolutionary. It learned to eat sunlight. It learned to take water and carbon dioxide and, using the energy of a photon, split them apart to build itself. This was photosynthesis. These microbes, cyanobacteria or blue-green algae, were wildly successful. They spread across the globe, but their new metabolism had a side effect. A waste product, a gas that was until then vanishingly rare in the atmosphere. That gas was oxygen. This gas was oxygen. Today we breathe oxygen as the very source of our vitality. But to the anaerobic life that dominated the early Earth, oxygen was not life. It was a poison. It was a violently reactive, corrosive gas that tore molecules apart. This cyanobacteria, in its success, unleashed the world's first and perhaps greatest pollution crisis. We call it the Great Oxidation Event. For millions of years, this new oxygen was absorbed by the planet itself. It combined with iron in the oceans, causing the seas to rust. This rust settled on the seafloor, forming the vast banded iron formations that we mine for steel today. They are the fossilized breath of these ancient microbes. Eventually the oceans were saturated. The oxygen had nowhere left to go but into the air. The atmosphere was forever changed. A mass extinction swept the globe, wiping out the life that could not tolerate this toxic new air. This new air also changed the planet's thermostat. The methane that once kept the planet warm was destroyed by the oxygen. The climate destabilized. The poles began to freeze, and the freeze did not stop. The ice advanced. As more of the world turned white, it reflected more sunlight back into space, making the planet even colder. This feedback loop ran out of control. The planet plunged into a profound deep freeze. We call this time Snowball Earth. It's possible the entire world was encased in ice, perhaps a mile thick for millions of years. From space, our vibrant blue world would have looked like a dead white cue ball. It seems like the end of the experiment, a world sterilized by its own life. But life is tenacious. Perhaps in the thin patches of ice near the equator or in the warm, dark oases of those hydrothermal vents, life clung on. And eventually volcanoes, continuing their relentless work, pumped enough carbon dioxide back into the atmosphere to create a greenhouse effect to break the fever. The world that emerged from the thaw was not the same one that had entered it. In the crucible of this global catastrophe, a new kind of life was forged, a new, more complex, more powerful kind of cell. We call it the eukaryote. Before all life was simple, a prokaryote, just a tiny bag of chemicals and genetic code. But the eukaryote was different. It was larger, it had compartments, it had a central nucleus to protect its DNA, and most importantly, it had a power source. It appears that in the chaos of this new oxygen-rich world, one cell tried to consume another, but instead of digesting it, a partnership was formed. The consumed cell was not destroyed, it became a permanent resident. This resident was a bacterium that knew how to breathe oxygen. It knew how to use that toxic gas to create incredible amounts of energy. This resident became the mitochondrion, a tiny internal power plant burning oxygen to fuel a cell 1,000 times larger. This was the spark. This was the invention. This new, energized complex cell was the ancestor of everything you can see without a microscope. It was the first cell that had the potential to become a mushroom, a tree, a fish, or a primate. The simple spark of chemistry born in a pond or a vent had survived its own poisonous revolution. It had endured a world of ice, and it had now created a new partnership. It was building a new kind of complexity. It was though it didn't know it on the long, slow path to building a mind. A consciousness that could billions of years later look back at the stars and try to piece together the story of how it all began. For billions of years, life on Earth was simple, slow, and small, dominated by single-celled organisms. But then around 500 to a million years ago, something incredible and mysterious happened. In a geologic blink of an eye, the oceans erupted with life. This event, known as the Cambrian explosion, wasn't a blast of vapor, but a burst of biological creativity. Suddenly the seas were filled with creatures that had hard shells, jointed legs, complex eyes and antennae. It was as if life's architect had thrown open the sketchbook, and the basic body plans for almost all animal life we see today, from insects to crabs to us, were first established in this remarkable period. Life had moved from simple to complex, and the world would never be the same. However, the story of life on this planet is not a simple straight line of progress. It is a dramatic cycle of creation and destruction. The universe, it seems, tests its creations. Our planet's long history is marked by several mass extinctions, which are like hitting a giant catastrophic reset button. These weren't slow, gradual changes, they were global catastrophes that wiped out the majority of all living species. The most famous of these resets happened 6 million years ago, marking the end of the Cretaceous period. For over 150 million years, the dinosaurs had been the undisputed masters of the Earth. They were the largest, strongest, and most successful land animals. They seemed unstoppable. Then a 6-mile-wide asteroid travelling faster than a speeding bullet slammed into the planet. The impact sent a shockwave of fire and dust across the globe, blocking out the sun for years. Plants died, the ecosystems collapsed, and the long reign of the dinosaurs ended in darkness and cold. They were gone. But extinction, while tragic, is not just an end. It is also an opportunity. When one dominant group disappears, it leaves a void, a new opening for life. While the dinosaurs ruled, a different kind of animal was hiding in the shadows, living in burrows and scurrying at night. They were small, warm-blooded, furry creatures, the first mammals. They were not strong, but they were adaptable. They managed to survive the asteroid's fallout. With the giant reptiles gone, the world was suddenly wide open. This was their chance. These humble survivors began to diversify, evolving to fill every empty role. They grew larger, smarter, and more complex. From these ancestors came whales, bats, tigers, elephants, and eventually a new kind of primate that learned to walk upright. This brings us to humans. After 4.5 billion years of Earth's history and 3.8 billion years of life, something entirely new emerged. It wasn't just another animal competing for food. It was a species that began to look at its own hand at the stars and at the cycle of life and death and ask the most powerful question in the universe: why? This is the most profound development in the cosmos' story so far. Through the long, slow process of evolution, our ancestors developed brains of incredible complexity. This complexity gave rise to self-awareness, the rich inner world of your thoughts and feelings. It gave us language, the powerful tool to share those complex thoughts with others, allowing us to build knowledge across generations. We are, as far as we know, the part of the universe that has become aware of itself. Think about that. The iron in your blood, the calcium in your bones, the carbon that forms your cells, these elements were not created on Earth. They were forged in the fiery hearts of stars that lived and died long before our sun was born. You are literally made of stardust. And now, after 13.8 billion years, that stardust has organized itself into a form that is able to think, to feel, to create art, to love, and to wonder about its own distant origins. We are the universe's way of understanding itself. This journey of awareness was not easy, and it certainly didn't happen overnight. For most of our history, we tried to explain the vast, confusing, and often terrifying world around us through stories. We created mythologies, epic tales of gods, goddesses, and heroes to explain the rising of the sun, the crash of thunder, and the mystery of death. We looked to the stars not as distant suns, but as a map of our own destiny. We developed astrology, believing the patterns of the planets held the secret to our future. In all these early models, we placed ourselves at the very center. Then, just a few hundred years ago, a mere eye blink in cosmic time, our understanding began a rapid and beautiful shift. A new way of thinking called science began to take hold. It was a simple, radical idea: we must follow the evidence no matter where it leads. An astronomer named Nicholas Copernicus proposed a shocking idea: perhaps the Earth moved around the sun, not the other way around. A bit later, Galileo Galilei used a new invention, the telescope, to look at the heavens. He saw moons orbiting Jupiter, proving that not everything in the universe circled the Earth. Finally, Isaac Newton gave us the mathematical laws like gravity that explained how the planets moved. This was a humbling moment. We learned that Earth is not the center of the universe. It's just one small blue planet orbiting an average star in a quiet suburb of a vast galaxy that contains billions of other stars. But this realization wasn't a loss, it was a liberation. It was the first time our species truly began to see the universe for what it is, not just what we wished it to be. The conscious cosmos had finally opened its eyes. And so our long journey through the cosmos, through the spirals of galaxies and the birth of stars, brings us to the edge. Not the edge of space, but the edge of time. We turn our gaze from the past, from the what is, to the what might be. We look into the deep, deep, deep future. For a long time we thought the universe was in a grand tug-of-war, gravity pulling everything in, and the momentum of the Big Bang flinging everything out. We wondered which would win. Would it all collapse back on itself in a big crunch, or would it expand forever, slowing down just enough to settle? And then we found something else, something hidden in the vast emptiness of space. We call it dark energy. It is not a thing like a planet or a star. It seems to be a property of space itself, a whisper of energy in the vacuum, and unlike gravity, which pulls this energy, pushes, it is a gentle, relentless pressure that is stretching the fabric of the universe apart. The most startling discovery was not just that the universe is expanding, but that this expansion is speeding up. The galaxies are not just drifting away from us, they are accelerating away from us. It is as if the universe itself has decided to grow faster and faster, pushing everything further and further apart. This discovery paints a picture of the ultimate future, not a future of fire, but of ice. It is called the Big Freeze. This is not an end that will happen tomorrow, or in a billion years, or even a trillion. The timescale for this is almost beyond human comprehension. It is a future so distant that the mountains on Earth would have worn away to dust, our sun would be a long-dead ember, and the stars we see now would be ancient memories. In this deep, deep future, the accelerating expansion will push all the other galaxies away from our own. First, they will fade, their light stretching and reddening, until they cross an invisible horizon faster than their light can reach us. One by one, the night sky outside of our own local group of galaxies will go dark. The universe will become a vast, lonely ocean of darkness with tiny islands of galaxies drifting alone, unable to see each other. Inside these lonely islands, the stars will slowly burn out. The great star-forming nurseries will run out of gas. The bright blue stars will die first, then the yellow ones like our sun, and finally even the dim red dwarfs will flicker and fade after trillions of years. The universe will be left with the ghosts of stars, black holes, neutron stars, and cold cinders, and even these will fade as black holes themselves slowly evaporate over countless eons, returning their energy to the void in a final faint whisper. The universe will not end in a bang. It will end in a long, slow, graceful fade into a cold, silent, and profound darkness. It is a sobering thought, a universe growing cold and empty, and it brings us to another question, one that we feel right now in our own time. In this vast cosmos, teeming with billions of galaxies, each with billions of stars, why do we feel so alone? This is the Fermi paradox, the great silence. If the universe is so vast and life had so many opportunities to begin, where is everybody? We listen with our radio telescopes and we hear only the static of the cosmos. We look and we see no signs of great galactic empires, no signals, no starships. There are many gentle answers to this question. Perhaps life is incredibly rare. Perhaps we are the first or among the first to wake up and look around. Perhaps the distances are simply too vast. Perhaps civilizations rise and fall like waves on an ocean never existing at the same time. Or perhaps they're quiet. Perhaps advanced intelligence learns to be contemplative, to look inward rather than shout into the void. We do not have the answer. And perhaps we never will, but the silence itself, it does not have to be frightening. It can be a way of understanding just how precious this moment is, how rare, how beautiful. This little spark of consciousness is here on our blue planet. Because that is our place in this story. We are not just in the universe, we are the universe. Think of it. The calcium in your bones, the iron in your blood, the carbon that builds your cells, every single atom in your body heavier than hydrogen and helium was forged in the fiery heart of a star that lived and died billions of years ago. You're made of stardust. We are the cosmos, made conscious. We are a brief fleeting moment, a part of the universe that has woken up and has the chance to look around, to wonder, to feel and to understand. We are the universe contemplating itself. We are its way of seeing the beauty of a spiral galaxy. We are its way of feeling the warmth of a sun. We are its way of hearing the silence of the deep future and feeling a sense of awe. And so as our journey comes to its end, let's return. Return from the edge of time, from the cold of the big freeze, from the silence of the star, and return to this moment, here, now. Feel the gentle pull of gravity holding you. A quiet reminder of your connection to the earth and to the entire fabric of space. Feel the breath moving in and out of your body, a simple, steady rhythm. The universe is vast and mysterious. Our time in it is short, but that does not make it meaningless. It makes it infinitely precious. You are a part of this grand cosmic story. You are a flicker of light in the beautiful unfolding mystery. Allow yourself to feel a deep, profound sense of peace. You are connected to everything. The stars are not just above you, they are within you. Let the questions fade. Let the vastness of space and time dissolve into a simple, comfortable darkness. The universe is vast, but you're safe. You're here, and now it's time to rest. Let the darkness be a soft blanket, a return to the quiet cosmos from which we came. Drift, float, and let go. Good night.